Okay, let's unpack this. We're diving into the 2024 Nobel Prize in Physics.
Right.
And it was awarded for work in artificial neural networks, machine learning.
Yeah, foundational work.
Exactly. So for a lot of you, I imagine the big question, the paradox really, is why did a prize in physics go to, well, the architects of modern AI?
It's a great question, and it really highlights this amazing bridge between fields. The Nobel went to John Hopfield and Jeffrey Hinton.
Right, from the early 80s.
Yeah, for discoveries back then. And machine learning, at its core, it's just the computer's ability to learn patterns from examples.
Like seeing tons of cat pictures and figuring out cat.
Exactly, instead of someone programming, step-by-step rules for what a cat is.
So how did physics get into it? How did they connect learning and memory to, like, fundamental physics?
Well, Hopfield's insight was really the key here. He took his background in physics, specifically the physics of collective phenomena.
Collective phenomena.
Yeah.
Like flocks of birds.
Oh, sort of, yeah. Or think about magnets. Billions of tiny atomic spins suddenly aligning, that kind of thing. He used the same mathematical models that describe those magnetic interactions to describe how artificial neurons could interact to form memories. It's pretty wild.
Okay, so from solid-state physics, magnets, to how a network remembers things, that's a leap. But hang on, if memory is like a low-energy state, like in a magnet, doesn't that mean it could be disrupted, by noise or heat, forgetting things? Did the model account for that?
It did, and that's kind of the beauty of using the physics framework. Hopfield saw computation or memory recall as the network settling into a stable state.
Okay.
Think of it like a landscape with valleys. A memory is a valley. When you give the network a clue, it's like putting a ball on the hillside.
It rolls down.
It rolls down into the nearest valley, the memory. That's convergent flow. And crucially, his model mathematically guaranteed it would find that stable, low-energy memory state.
Ah, so it addressed that stability problem early networks had.
Exactly. It equated reliable memory recall with finding the minimum energy.
It really underlines the value of looking across disciplines.
Yeah.
Where did Hopfield even come from to connect these dots?
Well, he was a bit of a polymath, really. Started in solid-state physics, yeah. Then he jumped into biology, studying hemoglobin, kinetic proofreading, weird stuff.
Okay.
Then he joined MIT's neuroscience program in the late 70s. He was always looking for this physics point of view, a quantitative way to understand complex systems, whether they were made of atoms or neurons.
And then came that famous 1982 paper. I heard there was a story about page limits.
Oh, yeah. It was for PNAS, the Proceedings of the National Academy of Sciences. They had a strict 5-page limit.
5 pages for that.
Right. He joked it forced him to write like Hemingway, super concise, leaving out anything almost obvious.
God.
But that actually kind of accidentally spurred the field on. People had to fill in the gaps, build on it. It created a community.
Okay, so Hopfield sets up this physics-based structure for stable memory. What about Hinton, the co-winner? Where does he fit in?
Right. So if Hopfield gave us the architecture, Hinton really gave us the engine for learning.
Ah, making the networks actually adapt.
Exactly. He used concepts from statistical physics, things like minimizing free energy, to figure out efficient ways to train these networks, especially networks with multiple layers.
So the algorithms that let them improve themselves from data.
That's the core of it. His work tackled the huge optimization problem. How do you adjust potentially billions of connections so the network actually learns? It paved the way for techniques we use today, like backpropagation.
And together, their work really forms the bedrock for a lot of modern AI, especially those recurrent networks, right, where information cycles back.
Absolutely. Hopfield's model was a precursor to the recurrent networks essential for processing sequences like language or time series data.
And these models aren't static, they've evolved.
For sure. The original Hopfield model, well, it couldn't store that much information relative to its size. But later work, I think it was 2015, Hopfield and another researcher came up with dense associative memory.
Dense associative memory. Okay.
Yeah, basically showing how to pack way more information into these networks, making that physics connection relevant even at the scale of today's AI.
So the big takeaway here seems to be physics isn't just about stars and particles, it's a way of thinking, a quantitative viewpoint.
Exactly. A viewpoint that can fundamentally reshape other fields like AI.
Which leaves us with a thought for you, the listener. The original Hopfield model, based on sort of classical physics ideas, had limitations in scaling and capacity, needing that 2015 update.
Right.
So does that suggest the next big leap in AI might come from physics principles that are maybe better at handling massive complexity or weird collective effects like, quantum mechanics, or maybe even something like fluid dynamics.
That's the question, isn't it? Where will the next physics-inspired breakthrough in AI come from? Something to think about.